Alright, today we're going to be talking about distance and a few proofs concerning more triangles. So first off, let's start with the definition of distance, which is simply the length of a segment connecting 2 points. So, any 2 points that are equidistant from the ends of the segment lie on the perpendicular bisector of the segment. Alright, so let's start with these 2 points, BD, and these 2 points are equidistant from the segment AC. Alright, so we're going to prove that BD is perpendicular, or no, AC is the perpendicular bisector of the segment BD. So, first we're going to say that both BC and DC are congruent, and AB and AD are congruent. Alright? So if AB and AD are congruent, and BC and CD are congruent, and AC is congruent to itself, therefore these two triangles are congruent by the side-side-side theorem. Alright? So let's keep going. These two angles, the ABC and ADC angles, are therefore congruent by the corresponding triangles theorem. And again, AE is congruent to itself, which is just that segment there on the left. So therefore, the BAE and the DAE angles are also congruent because of the corresponding triangles. Therefore, the ABE, AADE triangles, those two triangles above each other on the left side, are congruent by the SAS theorem, because we already stated that AB and AD are congruent, and AE is congruent to itself, and we have that angle in between those two segments, so we can say those two triangles are congruent. Therefore, BE is congruent to ED by the same corresponding triangles. Therefore, AC bisects BD. Alright? And then AEB and AED are congruent angles, also by the corresponding triangles theorem. And if there are two equal adjacent angles, then, and their sum is 180, they're right angles, since these angles lie on a line, or a line segment. Therefore, we know that they're going to equal 180 degrees. So therefore, AE is perpendicular to BD, and AC is the perpendicular bisector of BD. So moving on to angles, any point that is equidistant from two sides of an angle lies on the ray that is the angle bisector. So here we have point X, which is equidistant from the ray AB and the ray AC. Now if we take those line segments and make them perpendicular to the rays, we end up with two congruent triangles. And if we continue to do this all up and down the rays, then those points will form a ray that bisects the angle. Alright, let's talk about some circle proofs. Here are some things that we should know. All radii are equal. If two circles have radii whose lengths are equal, then the circles are congruent. And finally, a tangent line is perpendicular to the radius of the circle at the point of tangency. All right. So let's start with this circle. We have two tangent lines that intersect outside of the circle at point P. And then we're going to draw these triangles. We got AO and BO. They're congruent because they're both radii. Angle A and angle B are congruent because that is the point of tangency, so therefore they were both right angles, and PO is congruent to itself. Therefore, these two triangles are congruent by the hypotenuse leg theorem. And because now we know the triangles are congruent, we can say AP and BP, those two segments outside of the circles, are congruent as well. Now, with chords, if a radius is perpendicular to the chord, then it bisects the chord. All right, so here we have the radius OD and the chord AB, and they're intersecting at E, and it's a right angle since we are already given that. So with those two radii, we know that the radii are equal, and OE is equal to itself. Therefore, by the hypotenuse leg theorem, those two triangles are congruent. Therefore, AE and BE are congruent, and the radius bisects the chord. And with that knowledge, we can also say that if the radius bisects a chord that is not the diameter, it is perpendicular to the chord. And if the perpendicular bisector of a chord passes the perpendicular bisector of a chord passes through the center of the circle.